Hi folks, welcome back. So this is another data analysis video. Still talking about data transformation. So in the previous video, I demonstrated how to use different methods, create functions to impute or fill missing variables, missing values from variables in data set. We used the age variable from the Titanic data set, which has like 177 missing values. And we used a couple of different methods. One, we just replaced missing values with the median. One, we replaced them with a random sample. And what we found was that using a random sample seemed to help us improve it helped us improve the distribution of the data, and the data points after we'd filled those missing values with a random sample seemed to sit more neatly along this diagonal of observed compared to expected on this QQ probability plot. So what that demonstrated was it was kind of by using the method we used to impute allowed us to create a variable that was probably better suited to use in a parametric statistical model such as regression model or something like that. So using this kind of age variable where missing values have been filled using a random sample seemed to be a helpful thing to do. But what I'm going to do in this video is focus on a different variable from the Titanic data set that is very differently distributed. So the age variable it wasn't definitely Gaussian, normally distributed. It wasn't terribly skewed in any way either. But what we'll do is in this video I'm going to use the same diagnostic plots function that we generated here to sort of plot a histogram and a probability plot next to each other. But I'm going to use the fair variable. So let's call that, and you can see what we've got here is a very highly skewed, a very positively skewed distribution. So the histogram, you can see lots and lots of counts, low values, very few, and some one or two, maybe one even, extreme kind of like high values. So a distribution that deviates strongly from normal. So it's kind of not going to meet the assumptions that it needs to meet for use in some sort of parametric statistical model that assumes that the data we're using is normally distributed. And we can see that on the probability plot as well. It's kind of, these data points would need to sit neatly on this line. The more they do, the closer they're going to fit, the closer they're going to be to being meeting the assumptions of normality. And we've even got these extreme values up here that seem to be skewing things quite a lot. So we can improve the distribution of this variable using different types of transformation methods. And then we can visualize how the data has changed using this diagnostics plots function that I defined in the last video. Okay, so let's try a few different ones. So let's try the log transformation. So to log transform the variable, we're going to create a new variable and we're going to use the NumPy log transform. We're going to apply the NumPy log transform method to it. Okay, so here what I'm doing is I'm creating a new, on the data frame, I'm adding a new variable called log fair, so the log of the fair variable, and we're going to use np for numpy.log, and then we're going to pass the fair variable, the original variable, +1. So that is, the +1's kind of useful. You'll see when we get to the inverse, the reciprocal transform, the issues it can cause if we miss that off. But all I've done here is basically I've passed in the arguments that we need in order for NumPy to log transform the values. So remember, when we transform data, we're just applying some mathematical function to every score. So if I run this cell, we get a warning, but if we look at the data frame, despite the warning, it has actually created this variable, which now has the log transformed value of fair. So these values in the log fair differ from fair. They are the log transformation of that value. Okay, so let's now use this diagnostic plots function, and we're going to pass to it this log fair variable, and that's going to give us a histogram and a probability plot, so we can see how the distribution data has changed by applying this log transformation to it. And you can see already, compared to this, by log transforming the fair variable, it's already improved it. It's starting to look much more Gaussian, normally distributed, and these data points are much closer to the line, the diagonal line of observed against expected. So it's improved. That's a huge improvement. It's a big improvement on the original untransformed variable, and log transformation has here made the variable more Gaussian. But let's try some others, and we can decide which is the most useful, which is the best one to use. So another transformation that you can use is the reciprocal, and this just means the inverse. So we're dividing 1 divided by whatever our variable is. So the reciprocal transformation involves taking 1 over x, where capital X is the matrix of scores in our particular variable, or the vector of scores. Again, we're creating a new variable for the inverse of the fair. So I'm going to call this recip fair. So reciprocal of fair is the new variable. And to work out the inverse, we just take 1 divided by the original fair variable plus 1. So it's important here. I've added this plus 1. Notice that this is the denominator. It's under the division sign here. Without this plus 1, it creates a bit of dividing by values close to 0 creates an issue in that you can't actually divide by 0 because it's undefined, and it creates this kind of infinity problem. And it took me a little while to get this to work, and I was kind of missing off the plus 1, and it seemed to not be working properly, and it returned a message telling me that the scale was kind of infinity essentially, so it wouldn't plot anything on the scale. But plus 1 here seems to avoid this kind of infinity issue, this idea that you can't actually divide by 0. So let me run that. Gives us a warning again that it's kind of it seems to not like the way that I've done this, and we're saying you're setting a copy of a slice from the data frame, but if we look, it has actually worked, and we've now got a new variable, which is the reciprocal transformed fair variable here. And we can use diagnostic plots again to check what that distribution looks like. And if we look at that, what we see is it's maybe improved it a little bit compared to the original variable, but not a great deal. So it hasn't. If we look at the original distribution, it's slight improvement on this maybe, but not greatly. So it looks similar to the distribution of the original variable, and it's definitely not worked as well as the log transform that we've got here. Okay, let's try some others though and see if any others work better. So we can also do the square root transformation. This transformation, let me change the spelling here because I spotted that. So this transformation, it takes the square root of each value in the variable, okay? And we can conduct this manually by raising the values in the original to the half power. So all I'm doing here is I'm creating a new variable, square root of fair, passing the fair variable in, and this double asterisk is the exponent operator for Python, and we're raising it to the half power, which is the equivalent of taking the square root. Okay, so let's run this. Given us the same warning again, but it has worked. We've got our square roots for each of the fairs. We've now got a value that represents the square root of that fair. So let's look and see if that's any better using diagnostic plots. So it looks a bit better. So it's kind of shifted the distribution over to the right a little bit, and it's still very positively skewed. It's better than the original, and the data points are closer to the this diagonal line. But again, it's not. If we look at that and compare it to our log transform, it's not worked as well as the log transformation. Okay, so we're just working through and saying, well, which one's the best and which one would be better to use. So another one we can try is exponential transformation. So we can manually run the exponential transformation on a variable using a formula that raises the variable to the kind of 1.5 power. to all the kind of 1/5 power. So here what I'm doing is df exponential fair. So we're creating this new variable, and all I'm doing is to do that, to use the exponential transformation, is I'm raising each value in the fair variable to the 1/5 power. That should be 1/5, not 1.5, 1/5. Thank you. If I run that, it's going to tell us off again, give us this warning, but it has actually worked. And there you can see it's appended that to the data frame. So we've now got a fair variable, and so far we've transformed it using 4 different transformations: log, reciprocal, square root, and now exponential. So let's look at the diagnostic plots and pass this new exponential fair variable and see what that looks like. And that's a bit better. That's actually quite good. Yeah, it's done a good job of making the variable more normally distributed. It's shifted it across, if we thought of it like that. You can see a lot of these data points are now close to the line, this diagonal line. So it has had a similar effect to log transformation. I don't think it's quite as good as if we compare that exponential, scroll up, let's look at the log, to the log transformation. They're both pretty good, but I think maybe the log transform has worked a little bit better. But anyway, okay, so far 2 of them seem to work quite well, 2 of them haven't done a great deal. One more we will try though is the Box-Cox transformation. So this is a very common transformation method when you're fitting linear models. So in order to use this transformation though, the data needs to be positive. There need to be no negative values, and it also needs to be continuous. So you can't have discrete scores, it needs to be measured on a continuous scale. That's okay for us for this fair variable because it's measured using decimals to quite precise values. So whereas with the ones above, I have kind of manually used the calculation in order to do the Box-Cox transformation. What I'm going to do is use the Box-Cox method or function from SciPy stats. Okay, so I imported SciPy earlier at the start of the previous video, and what I'm going to do is create this new variable, df Box-Cox. I'm going to pass the parameters are equal to stats.boxcox, and then we're passing df.fair plus 1. And what I'm going to do is print an optimal lambda and the parameter. If I run that, it gives us some optimal lambda value. And if I print the head of the data, we should be able to see that we've now got this new Box-Cox. I'm not going to say too much about the lambda parameter and stuff like that here. I think I'll cover that again. I'll cover that in more detail at some future time. But the main thing to know here is that using SciPy, I've asked it to print this and print the parameter that it's going to return, and create a new variable in relation to it. It has created and appended this new Box-Cox transformed version of the fair variable. So let's pass that into our diagnostic plots function. This is what that looks like. And again, that's pretty good as well. So it's similar to exponential and log transform. It's kind of made the distribution much more Gaussian. A lot of these data points are close to the line. It goes off a little bit at these lower end of the values. They seem to deviate quite a bit. So using Box-Cox transform has improved the distribution of the fair variable considerably. It looks more Gaussian, and it would be a judgment call as to which transformation to use. If you were going to use the fair variable in some sort of parametric type model, such as a linear regression or a multiple regression, you'd be making a decision as to which one to use. The 2 that look to have been the most effective on this variable, fair, seem to be log transform and Box-Cox, so you could probably use either one of those. Anyway, that's all I'm going to cover on data transformations in this video. So what I've demonstrated here is if you've got a variable that's not normally distributed but you need it to be, or it'd be better if it was, there are a number of options open to you. So this was a highly positively skewed variable fair, and we transformed it in a number of ways, and we assessed which one improved the distribution so it looked more like a Gaussian distribution, so we could include that in the model. So something to consider though is when you can transform a variable, and you include the transform variable in your model, what you are assessing is the relationship between that transform variable. So it could be the log of fair, or it could be the square, squaring the exponent, an exponential version, or it could be the Box-Cox. It's not the original data points that have been changed in some way. So that needs to be clear that it's a log transformed variable. Okay, so there are lots of arguments for transforming your data in different ways. In some ways, if you're absolutely wedded to using models that assume a Gaussian distribution, and you don't have data that is, in some ways you're forced really to try data transformations in some way. I've been criticised in the past for not using them. There are arguments for and against it, I think. Hopefully this was useful and interesting. I'm going to record another video where I'll kind of demonstrate these sorts of things again, but using NumPy. So using NumPy to conduct the transformations rather than me manually showing the mathematical functions. Okay, so that's enough talking from me, I think. Hopefully this was useful. One more data transformation video coming up, and then I'll move on to something else.